Okay, thank you very much for the introduction. And yeah, today we are going to talk about hypervisor fuzzing. Okay, so, well, first of all, the motivation. Hypervisors have evolved to, well, actually become the foundation for modern cloud computing environments, or the modern cloud computing world. And hypervisors do also provide the ability to run software inside virtualized, isolated environments, as well as the ability to share physical resources across multiple virtual machines. And well, of course, there is some kind of need for a secure implementation, but unfortunately, most hypervisors are implemented in memory-unsaved languages, such as C, C++, and parts are even written in assembly. So yeah, what's the threat model? Let's assume there are two virtual machines. And let's assume that at some point during execution, an attacker is able to gain code execution at the second virtual machine. And this is basically, from now on, we can assume that this virtual machine is has become a malicious guest. And if we assume that this malicious guest is privileged, which means the attacker is able to execute code in kernel mode, ring 0, and if you assume that there are implementation flaws, security vulnerabilities in the hypervisor implementation, well, then there are multiple possible attacks. First of all, very simple, an attacker might be able to just crash the virtual machine itself. It's not the same as crashing the operating system because there is a distinction, but it's still not that interesting unless it's a deadlock or an infinite loop, which will result in some kind of resource exhaustion in terms of CPU time, right? But what if we can move this attack to another virtual machine? So we are able to crash another virtual machine, which would basically a remote virtual machine in our service attack be. And even worse, if there are critical vulnerabilities in the implementation, then an attacker might be able to get code execution at another or inside another virtual machine. It's basically a virtual machine escape to another guest. And since we can assume that the hypervisor might contain or might has some secure contain some critical vulnerabilities, we can also apply all those attacks to the hypervisor layer. So it's possible to crash the hypervisor, and unfortunately, if you're able to crash the hypervisor, a host denial of service will result in a kernel panic or in a crash of the physical machine, and the same will happen with all virtual machines. So, and the worst case scenario is basically if you're able to escalate privileges to the hypervisor layer, and then it's basically, it's game over, right? And Microsoft is aware of the possibility of such critical vulnerabilities, and if you are able to find critical vulnerabilities in their hypervisor, Hyper-V, well, they offer a bug bounty up to $250,000 US. So it seems like it would be nice to use fuzzing, right? Since fuzzing is a good or is a great technique to uncover bugs. But unfortunately, it's not so simple. Well, so let's talk about user space fuzzing. User space fuzzing is simple, right? There is a fuzzer, and well, the tools are there. We can use AFL, HongFuzz, and so on. And there's a target application. And the fuzzer will basically generate data provided to the target application. And since fuzzers are good at finding bugs, well, at some point, the fuzzer will succeed. And yeah, that's it, basically. So user space fuzzing is simple, simply because the interfaces or to interface with the target application is simple as well. So you can just write data to a file or just write data to a pipe, and that's basically it. But unfortunately, it's not so simple for hypervisors. There are different interfaces, and it's not so easy to port a user space fuzzer to a specific hypervisor, and so on. There are challenges. But first of all, just let us talk about the attack surface of hypervisors. So first of all, there is a guest, a virtual machine, and a hypervisor. And well, if we are able to run operating systems such as Linux or Windows inside a virtual machine, then at some point the guest will try to execute a privileged instruction. And well, a hypervisor simply cannot allow it to execute a privileged instruction in the context of the host. And well, therefore, there will be a special virtual machine exit transition between the guest and the hypervisor, and then the hypervisor starts to emulate stuff, and then the execution goes back to the guest. And this approach is called trap and emulate, and well, it's utilized virtually by any hypervisor available. So it's like if there is an exit reason, you just trap and emulate everything and so on. So as you can see, here's an example. The guest tries to execute the move CR4 instruction, and I don't know, writing to a control register is not a good idea. So there is a trap, an emulation request. Everything is handled in the hypervisor, and then we can continue. And there are other interfaces which behave in the same way. So if you want to provide emulated devices such as VGA, PCI devices, and so on, well, so you have to implement some kind of memory map I/O capabilities, since those emulated devices rely on memory map I/O to interface with the guest. And memory map I/O is actually quite simple. You're just writing or reading from a specific address, and then a trap will happen, and basically the device emulator takes care. Same for port I/O, it's just the same as memory map I/O, but in a different address space, and you have to use instructions like in and out. It's just there because if you want to boot a 32-bit operating system, well, you rely on hardware which only provides or which only interfaces via port I/O, like the timer or interrupt controller. Then what about hypercalls? Maybe there are hypercall interfaces, and if you communicate with an emulated device, maybe at some point the device will try to read and write data from the guest, so direct memory. And if we're able to figure out where the address is, maybe we can put some data there and hope for the best. So, our implementation. Well, first of all, those are our goals. We wanted to build a hypervisor fuzzer which works basically with any x86 hypervisor. And we achieved that by implementing a special operating system with one purpose, to fuzz hypervisors. And the requirements for a hypervisor are simple. The hypervisor has to provide the ability to boot from an ISO file and the ability to boot from BIOS or UEFI, so nothing special. And instead of utilizing coverage-guided fuzzing techniques, we instead build our fuzzer as a black box fuzzer, and there's a reason for that. First, if you want to support closed source hypervisors, it's actually almost impossible to trace the hypervisor, the closed source hypervisor, in an efficient and fast way. Second, if you rely on black box fuzzing, then you can implement something which we called high throughput. You can basically accelerate fuzzing if you don't care about coverage informations and so on. And we also wanted to build a fuzzer which is able to fuzz multiple interfaces and perform different operations on those interfaces. So here we go, our approach. There's a hypervisor we want to test. Then we ask the hypervisor to create a virtual machine. Then we ask the hypervisor to boot our operating system, which in this case is Hypercube OS. And after the boot process, basically Hypercube OS will perform the interface enumeration procedure, which basically means that our operating system will scan for available interfaces, such as PCI devices, hypercalls, core components, such as timers or interrupt controllers, and so on. Later on, the information is passed to our fuzzing engine. And, well, our fuzzing engine is actually just a bytecode interpreter, and the name is Tesseract. And, well, we just execute different handlers during fuzzing to perform different operations on different interfaces. Well, we implemented some handlers, such as the ability to write to a MMIO region, to read from a IO region, or to perform or to erase hypercalls, write MSRs, stuff like that. And, well, the implementation is actually quite simple. So we utilize a simple PRNG, a pseudo-random number generator, which generates just a stream of data. And at some point, we just translate everything to a sequence of handlers which we execute. And, well, from a high-level perspective, that's it, actually. So the evaluation. Since we are able to target multiple hypervisors, yeah, we've tested the following. So FreeBSD Beehive, KVM QEMU, VMware Fusion, and so on. And yeah, here we go. Those are our results. So we were able to find 55 different bugs in different hypervisors. And in total, I guess 43 CVEs were assigned. So, and I want to show you just one simple, but at the same time, critical vulnerability. So we found host denial of service in the Beehive hypervisor. So Beehive is the standard FreeBSD hypervisor. And this is the payload found by our fuzzing operating system. And there is a configuration for the interpreter. And in this case, we will only focus on one specific region, the APIC region. And APIC stands for the Advanced Programmable Interrupt Controller. So it's basically the interrupt controller. You don't want to mess up with the interrupt controller because, yeah, it will result in some kind of crashes of your own operating system. But we designed several parts of our operating system in a way that we don't care, and the worst thing that could happen is basically a triple fault, so then we reboot and continue. And by doing so, we were able to find this payload. We have to execute one specific opcode, MMIO memset32. And this opcode translates to this to those four instructions. And basically, we are using a moveS instruction. And moveS is basically, it's memcopy implemented as an instruction. So you can put something in the EDI register, it's the destination, ESI, the source, and ECX, the count. And if you perform, or if you execute this instruction, and you're targeting the APIC MMIO region, well, the host will crash. And what's the reason? Well, it seems like there is an issue in the emulate moveS instruction, so there's an unexpected error. And what we found was basically, if you write or if you use the moveS instruction to write to MMIO region, it will always work like a charm, except for the APIC. And the reason is simple. Only the APIC is inside the kernel, because of performance reasons. So if a device emulator is in the kernel, this will happen. And we also performed some experiments on the rediscovery ability of well-known bugs, such as the VENOM vulnerability. And 5 years ago, this vulnerability was discovered in QEMU and Xen and KVM, since all of them are built upon QEMU, and it's basically a memory corruption inside the floppy disk driver. So, using our operating system, running in TCG mode, in emulation mode, it takes 6 seconds to find the bug. If you run everything in KVM mode, so it's the hardware-assisted virtualization mode, then it will take 50 seconds, and the reason is simple. It's basically because hardware-assisted virtualization is not optimized for high I/O loads. But yeah, 50 seconds. And we also evaluated our approach against another approach, which is AFL-based. So it's an AFL fuzzing approach to fuzz specific device emulators in QEMU in isolation. Not the full system, only specific device emulators. And well, we did the same experiments. And yeah, we performed the evaluation on 15 device emulators. And here we go. In 13 out of 15 times, our approach was able to find more coverage. Same for the ability to find crashes. And what's interesting is basically that with our approach, we just run our fuzzer for 10 minutes each, whereas the AFL-based approach performed around 50 to 60 days. It really depends on the target. So, to conclude, in our paper, we described a novel technique to fuzz hypervisors in a very efficient way so that you can target actually all x86 hypervisors. And by implementing this high throughput mode, so we're able to outperform, at least on some experiments, coverage-guided fuzzers. And yeah, if you also fuzz the whole system, you're also able to catch nice bugs like the Beehive host denial of service. And yeah, that's basically it. Thank you for your attention, and I'm ready to answer your questions.
Yes, Heng.
Thank you for mentioning my paper, VDF.
I'm sorry.
I was really curious. I mean, so you said that your system outperforms VDF. You got faster cover. I mean, finding more crashes, more coverage. So is it simply because of much higher throughput? Do you have a number like comparing with the VDF's approach? How many? How much faster is your fuzzing?
Yeah,
system?
unfortunately, there are no numbers in the VDF paper, so it's hard to compare. But it's just we believe that's the reason. Yeah, maybe we can discuss later on. But actually, we really believe this is the reason because in our experiments it's super fast. So there are no delays. You can generate up to 64 million opcodes without the overhead of the hypervisor. But yeah. We also noticed that in two examples, SDHCI and another device, we were not able to find more coverage simply because those devices are really complex. And I believe that this is a field where an AFL approach would really help. So there are limitations.
OK, thanks.
Other questions?
Hi, I'm Fabio Gritti from UCSB. I didn't get why you had to implement a custom operating system compared to just writing a kernel module that can access the emulated devices.
Yeah. Well, there are some reasons. First of all, we want to build something which provide a good ability to reproduce crashes, since we noticed that sometimes it's really hard if another driver is interfering with some components. And second, just think about the Beehive crash. Writing to an APIC region, it's like the operating system will crash. And our actually operating system is optimized for such use case. And yeah.
Gotcha.
Okay,
thank you.
Yep.
Thank you. Hi, my name is David Gens from UC Irvine. Great talk, thank you.
Thank you.
I just have a question regarding the QEMU version. It's rather old. Is there a particular reason for that?
Yeah, we wanted to perform the same experiments as described in the VDF paper.
So this is just for reproduction.
Yeah, right.
Did you try that on a more recent version?
Yeah, and we found some. So the bugs are in the paper. So some memory corruptions, deadlocks, assertion failures,
Cool.
stuff
Okay.
like that.
Thank you.
Cool. Let's thank the speaker again.